Hello everyone, let's learn about the applications of Gauss theorem. The first application is to find electric field due to a continuous charge distribution on the straight conductor, a wire, straight wire as shown. Here Gaussian surface is cylindrical, which is around that wire and is taken in such a way so that we can find the total flux. Total flux will be the sum of three fluxes through three areas 1, 2, and 3 as shown. Through first area, the angle between electric field and the area vector is 90, and at second area the angle between electric field and the area vector is 0, and third again it is 90-degree angle. So we will get the flux through only curved surface area, which is 2 pi rl as shown. And by applying Gauss theorem we will reach to the final result. Gauss theorem states the total flux is equals to q by epsilon naught, and the total flux is E into 2 pi rl, and we have found the final result. Now this is prototype model where this is a wire and this transparent cylinder is the Gaussian surface. So this wire is at the center, and if electric field is there, the flux will be passing only through the curved surface area. There will be no flux through the circular areas of the cylinder. It can be understood through this prototype model that flux is only through the curved surface area, not through the circular areas. Now, second application, to find the electric field due to a sheet, positively charged sheet as shown. Here again, the Gaussian surface is taken cylindrical to make the mathematical calculations easier. Here the flux will be through circular area, and through curved surface area flux will be 0. It can be calculated mathematically. Same total flux is sum of three fluxes through first, second, and third areas. At the first area and the third area, the angle between electric field and the area vector is 0 degree, and through curved surface area, the angle is 90 degree. So curved surface area will not contribute to the flux. Flux will be 0, and two fluxes will be added through two areas that are pi r square area of circle, and we will get the total flux. Then by applying Gauss theorem, the total flux is equals to q by epsilon naught. We will reach to the formula of electric field due to this sheet, that is q upon 2 pi r square epsilon naught, where we have put the value of surface charge density, and the final formula is sigma upon 2 pi 2 epsilon naught. That is for thin sheet, and for thick sheet two values will be added and the formula will be sigma upon epsilon naught. Now there are two more arrangement. There are two positive sheets are placed parallel to each other, and at three different points the net electric field can be found by using superposition principle. At the left, electric field is added and it is sigma upon epsilon naught. In the middle, both the fields are subtracted because both are in opposite direction if net field is 0, and at the right then again electric field is added, and magnitude of the electric field is sigma upon epsilon naught. Now if one is positive and one is negative, then at the left net electric field will be 0 because both are anti-parallel fields. In the middle, both fields are added because both are parallel fields, or magnitude will be sigma upon epsilon naught. And at the right, both the fields are in opposite directions, that is why net field is 0. And this is the condition of a capacitor as well, that we'll study later. Now this is a prototype model of this infinite sheet. There is a positively charged sheet, and this red colored cylinder is the Gaussian surface. And again, only circular areas will contribute to the flux here, as we have discussed, and curved surface area will not contribute to the electric flux because no electric field line will cross through the curved surface area. that can be understood by this model. And there is one picture where it is shown electric field lines are crossing through the circular area, not through the curved area. Now the third application, where electric field due to a spherical shell can be found, and there we have drawn three Gaussian surface. One is at outside, one on the shell, and one inside the shell. R less than R means observation point is lying inside the shell. So there again, according to Gauss theorem, total flux is equal to q by epsilon naught, but q is 0 inside the shell, so net field will be 0. Then second, on the surface, there q enclosed is q on the shell, and net electric field is coming out to be integration of ds is 4 pi r square, and e is q upon 4 pi r square epsilon naught, where small r is equals to capital R. Then at outside point of the shell, there again the field will be, the charge will be same q, but the field will be q 4 pi epsilon naught r square. Here in the graph between electric field and r, electric field is 0 at small r less than capital R, then it will reach to the maximum value on the surface, and outside the shell it decreases inversely with r square as shown. Now the Gaussian surface we have taken, which is spherical in nature in this derivation. So this is open surface which can be closed by making it a sphere like this, which we have used as a Gaussian surface in this derivation. Thank you.